This lecture is about the simplest type of image you could use in computer vision, which is called a binary image. A binary image can have one of two values, 0 or 1. For instance, you see this image here, you have 1 for object and 0 for background. As you can imagine, these are images that are very easy to process, to store, and to analyze. But it turns out, as simple as they are, they're extremely useful. There's lots of things, especially in structured environments, that you can do very efficiently, very robustly using binary images. So how do we make a binary image? Well, you take a gray level image, that's just a brightness image, that's g of xy right here, and you simply threshold this gray level image with some predetermined threshold, either automatically computed or set by the user, and you get what's called a characteristic function, also called an indicator function, bxy, where bxy is 0 if the gray level image is less than the threshold, and it's equal to 1 otherwise. Or it could be the other way around, doesn't really matter. So how do you set this threshold? Here is a gray level image, and if you first compute the histogram of this image, the histogram is shown right here. You have gray levels from, say, 0 to 255 on the horizontal axis, if it's an 8-bit image. And for each gray level, you have the number of pixels in the image that have that gray level. That's the histogram. And you see that the histogram has two modes. One mode corresponding to perhaps the background, and the second one corresponding to the objects in the image or the foreground. And between these two modes, you have a valley, and that is where you would pick your threshold. The gray level corresponding to the valley would be a good threshold to use. And when you use that threshold, you end up with a binary image that looks like this. A pretty clean image that's ready for processing now. So, as you can imagine, binary images are useful in many different domains, not just circuit boards as shown here, but fingerprint analysis. In the case of fingerprints, you want to look at the curves and ridges in your finger. You use some special lighting to capture an image of the fingerprint, and then you binarize it or threshold it. Another example widely used is visual codes like QR codes. In this case, you have a pattern, you find the corners. Once you have that, you literally go in, threshold the image, and read out the bits, ones and zeros. And they can be used in other domains as well. Showing an example in medical imaging where you're looking at the structure of the bone, say, for instance. It turns out that binary images are useful also in the context of three-dimensional objects. So take a look at this object right here. If I simply drop the object, it's going to fall down on my palm. Imagine this to be a plane just that the object sits on. And it falls in one of its what's called stable configurations. If I use another position, it's going to fall in a different stable configuration. So it turns out that most objects, irrespective of how complex they have a finite number of stable configurations. This is very useful. So because if you imagine that you have a plane and you have three-dimensional objects sitting on that plane, and you're imaging this plane from the top, then it turns out that this camera is going to see the objects in one of their stable configurations. Of course, the object can be translated, it might be rotated, but it's still in the same stable configuration in terms of the contact points that it makes with the surface. So, what you could do is essentially drop all your objects on a plane and take an image like this, and then try and create a binary image from that. And then you can recognize these three-dimensional objects from these two-dimensional images. Unfortunately, as you can imagine, it's going to be really hard to threshold this image to get a binary image. You see that some of the objects, because they're 3D, have shading on them. They have these strong specularities or highlights. They have different colors. In fact, if you look at this object right here, a part of it is virtually the same brightness as the background itself. So simple thresholding is not going to work. So for applications where binary images can be really useful and where the lighting can be controlled, it turns out that you can create a setup, an imaging system, which almost directly gives you the binary image. What you do is you use what's called backlighting. This is a light box. We can use it as backlighting, and you would place your objects on this lighting system and then take an image from the top. And when you do, you're going to get a very nice, clean silhouette of the object. And that's what I've done here. If you take a look at this image, this is taken using the same backlight that I just showed you and the same objects. And you see that without any processing, you get almost the image that you're looking for, a binary image. So, we're going to be talking about, in this lecture, the processing of binary images. Like I said before, a binary image can have only one of two values, 0 or 1. And so first we're going to be talking about geometric properties of a binary image of a single object. We're going to start with just one object and say what are the properties we can compute from its binary image that allow us to figure out where it is and what its properties are which are invariant to translation and rotation so that we can distinguish the object from other objects, that is recognition. And then we'll look at the problem of segmentation, that is, and binary image may have multiple objects inside of it. We need to label these objects as being different before we compute their geometric properties. So we'll look at a couple of different algorithms for very quickly, very efficiently labeling a binary image and thereby segmenting it into different objects. And then we'll talk about the problem of iterative modification. Imagine you're given the binary image of an object and you want to find its skeleton by thinning the object. This is the kind of operation that you can actually conduct by applying a simple algorithm to each pixel in the image in parallel, and then taking the output and feeding that in as the input again. So iteratively you modify the image to take the initial image and thin it down to a skeleton. And when you do that, you want to make sure that you don't change the structure of the object. Morphologically, you're not introducing new bodies and holes in the image. And so we look at what it means to do iterative modification while being conservative in the way that the processing happens.